So today we're talking about section 8.7, surface area. Start with the definition of surface area. The surface area is the sum of the areas of all the faces or surfaces that enclose the solid. Important to note here that area applies to a two-dimensional figure. Surface area applies to a three-dimensional figure. That's why they say that encloses the solid, because it's a three-dimensional figure. For prisms and pyramids, the faces include the solid's bases and its lateral faces. It's almost like a little nursery rhyme there. For prisms and pyramids, the faces include the solid's bases and its lateral faces. Yeah, it's perfect for Dr. Seuss, right? He had his birthday last week. So here we look at some of those bases and lateral faces. On the left, we have a prism, right? And each lateral face is a rectangle. And the bases of this lateral prism are hexagons on the top and the bottom. So we would call that a hexagonal prism. On the right, we have a pyramid, and its base is a pentagon, so we would call that a pentagonal pyramid. The lateral faces of the pyramid, as you can see, are made up of triangles. So this slide sort of just shows us some applications of surface area. This is all architecture, some famous buildings, some of which we know right here in Pittsburgh, the PPG building. The surface is covered in glass, so certainly somebody needed to know how much glass was needed in order to surface that building. So surface area would have been very important there. We have the Louvre in Paris, France, up in the top middle. Again, all glass. An interesting looking house here in the bottom middle. It says a cone is part of the roof design of this Victorian house in Massachusetts. Think if you were hired to paint that house. I mean, look at all the paint colors on that house. You certainly would need to do some good calculation of how much paint would be needed. And then on the right, this stone tower is a cylinder on top of a larger cylinder. So certainly you'd need to calculate the surface area to determine how many bricks you would need, right? So very common applications of surface area in architecture. All right, so now we get into the formulas for surface area, some of which are quite simple and very straightforward. Others, perhaps not so much. So let's get to it. The surface area of a rectangular prism. So if we take the rectangular prism that we see on the left and we break it into its different pieces, that's what we're getting on the right. Of course, the top and the bottom will be congruent to one another, and in this rectangular prism, they have length and width of 8 and 6. And then we have the front and back that would be congruent, as well as the left and right sides being congruent. The front, you can see here, has dimension 6 by 3. The back would be congruent to it, right? So we account for that here and here. And then we have the left and right sides. So the left side would be back here. That would be 3 by 8. And the right side, 3 by 8 again. And of course, they're being accounted for here and here. So in a rectangular prism, of course, we have a bunch of rectangles. And we know the area formula of a rectangle is length times width. So to come up with the surface area formula of a rectangular prism, we just need to double a lot of these rectangles, right? For the front, length times width. For the back, length times width, so 2 times LW. Then for the left and right sides, length times height, so double that. And then for the top and bottom, width times height, times 2. Now, of course, for a shape like a rectangular prism, you don't really need to know a formula. You just need to be able to calculate the area of each side and then add them all together, right? So in some cases, a formula for surface area is a little arbitrary. It's not absolutely necessary. But in others, as I think you'll see soon, having a formula is necessary. So next we take a look at the surface area of a cylinder. So we have the cylinder on the left, and on the right we're going to break it apart into its pieces. Of course, with a cylinder, the top and the bottom are congruent circles. And that's what we see here and here. We know the area formula of a circle is pi r squared, so that's going to play into our surface area formula for a cylinder. Now it's this middle part here in the cylinder. And of course, that middle part is curved, right? How do we calculate the area of that curved middle part? Well, the best explanation I have is think of a soup can, right? A soup can has a label on it. If you were to slice that soup can label directly down the middle, perpendicular to the bases, and take it off of the can and unfold it, it would become a rectangle, like we have right here. We know the area formula of a rectangle, length times width. But we can't call it length and width because a cylinder doesn't have a length and a width, right? What becomes the length of the rectangle is the circumference of the cylinder. Because remember, that soup can label has to wrap itself all the way around, right? Therefore, we have 2 pi r as the length of the rectangle. The width of the rectangle becomes the height of the cylinder. So we have the width of the rectangle as h. Now let's put all this together. We have a top and a bottom that are both circles, and then we have a length and a width that are 2 pi r and h. So when we put it together, we have 2 times pi r squared plus 2 pi r h. I think this is an example of a shape where we start to see the value of knowing a formula, right? Or at least understanding that formula. The next one, surface area of a pyramid. So pyramids can have bases that are any polygon. So we need to know the formula for finding the area of any polygon. Now what we can remember here, though, that the pyramid usually has a base that is a regular polygon. And we learned the area formula of a regular polygon. So in this case, it looks like we have a base that is an octagon, right? Now, pay close attention to the way that this pyramid is labeled. They are telling us over here that the side of the base, the sides of the base, have a length of b. Okay? Now, look at the lateral faces of the pyramid. We said before that all the lateral faces are triangles. Well, we know the area formula of a triangle, 1/2 base times height, right? In which case, the length of the base of the triangle is equal to the length of a side of the base. That can get confusing, so pay close attention, right? So what the length of a side of the base was b, and the length of the base of one of the triangles is b. Now, the height of the triangle is not the height of the pyramid, because, of course, each lateral face of a pyramid slants in, right? So the height of the actual pyramid would be somewhere here, and it would go right up the middle of that pyramid. But the height of each triangle starts out here on the base and then slants in towards the vertex at the top of the pyramid. So don't get the height of the pyramid confused with the height of one of the triangles. Keep that clear. In our diagram, we see that the height of the triangle is being called L. Okay, so now let's piece together this formula. It's not that hard. The area of the base, that is a regular polygon. Well, we know the area of a regular polygon formula is 1/2 the apothem times the side length times the number of sides. But in this case, the apothem, they're calling it A right there, so that's fine. We'll keep that in A. But they're calling the side length B, so we better put a B in here. So now we have 1/2 ABN for the number of sides. Okay? Now the area formula for a triangle we know is 1/2 the base times the height. Well, in this case, the base is called B, so we'll leave the B in there. But the height is called L, so we better change this to 1/2 base times L. Times the number of triangles there are in a pyramid, which will be equal to the number of sides there are in the base. So we better multiply this over here by n. Now add these together, and we have the formula for the area of a pyramid. All right, the last one here is the cone. All right? Now the cone is one that you definitely need a formula for, because it's not like you just have different surfaces that you're going to find the area of and add them together. So let's think about the cone. Well, of course, the cone has a circular base, and we can find the area of a circle, pi r squared. So that's kind of taken care of. We know that our formula will have pi r squared in it. But what about the actual cone part of it that is circular? How in the world do we find the area of that? Take that cone piece, and again, like our soup can label, let's cut it. And let's unravel it. And what happens is it takes the shape almost like of a fan, you know, those old fans that you spread out and then you fan yourself with. Well, that's kind of what it looks like, right? But mathematically, geometrically, that's a sector. Yeah, that's a sector. All right? So if we take that sector and we break it into a bunch of little slices, almost like we did with a circle, and we take these slices that are almost triangles, and we arrange them next to each other to create a rectangle, we can apply the formula for area of a rectangle, which we know is length times width. Now, this distance right here is the distance that had to wrap around the entire base of the cone. That's why we label it as 2 pi r, because it's the circumference of the base. Now, this distance right here is the diagonal height of the cone, right there. And we're calling it L. You can see L right there. So when we rearrange these slices into a rectangle, we have half of the circumference as our length, pi r, and we have L as the width of our rectangle. So to create our formula for surface area of a cone, we have the circular base, which is pi r squared, and then we have length times width, which is pi r L. So as I said already, in some solids, surface area is as easy as finding the area of each surface and adding them together. In other solids, like the cone and like the cylinder, having a formula can be very helpful and almost absolutely necessary.